Hello everyone, welcome back to the Key Concepts in System Design course. Today we're going to dive into the ACID properties of databases. ACID properties are the foundation for ensuring the reliability and consistency of database operations. For anyone involved in system design where transaction handling is crucial, understanding ACID is essential. So, what exactly is ACID? ACID stands for atomicity, consistency, isolation, and durability. These four properties work together to ensure that transactions in a database are processed reliably. Let's break down each of these properties in detail. Let's start with atomicity, the A in ACID. In simple terms, atomicity means that a transaction is indivisible. All operations within it must either be completed successfully or not at all. If any operation fails, the entire transaction is rolled back, returning the database to its previous state. Whether a transaction has one or many operations, they must all succeed or none at all. There's no middle ground. This is the essence of atomicity. Let's consider a simple example of a bank transfer. Imagine John has $3,000 in his account and Tom has $1,000. John wants to transfer $500 to Tom, initiating a transaction in the bank system. This transaction involves two main steps. Step 1, deduct $500 from John's account. Step 2, add $500 to Tom's account. If both steps are completed successfully, the transaction is committed and the transfer is completed. John's account balance becomes $2,500 and Tom's account balance becomes $1,500. However, if any step fails or the transaction doesn't meet certain conditions, the entire transaction is rolled back. As a result, both John's and Tom's account balances revert to their original states. John still has $3,000, and Tom still has $1,000. John doesn't lose any money, and Tom doesn't gain any extra money. In MySQL, when using the InnoDB engine, atomicity is achieved through the undo log mechanism. MySQL records the rollback operations corresponding to each step before the transaction starts. For example, for the first step, where $500 is deducted from John's account, MySQL records the old balance of $3,000 in the undo log. If the transaction is rolled back, the rollback operation will restore John's balance to $3,000. For the second step, where $500 is added to Tom's account, MySQL records the old balance of $1,000 in the undo log. If the transaction is rolled back, the rollback operation will restore Tom's balance to $1,000. In summary, atomicity ensures that all operations within a database transaction either take effect completely or not at all, ensuring data consistency and reliability. Next, let's talk about consistency, the C in ACID. Consistency ensures that a database remains in a valid state, meeting all defined rules and constraints before and after a transaction. Although a database might temporarily be in an inconsistent state during a transaction, it must return to a consistent state by the time the transaction ends. Consistency in a database can be ensured in several ways. First, there are built-in constraints. These are the rules enforced by the database system itself to maintain consistency. For example, primary keys must be unique, meaning no duplicate values are allowed for primary keys in a table. Additionally, foreign key constraints ensure that the referenced records exist. Data type constraints are also important, such as ensuring that a date field only accepts valid date formats. Second, there are business rule consistency checks. Some consistency rules are defined by business logic and need to be implemented through code or extended database functionalities. Let's look at a specific example of business rule consistency. Imagine you are managing the inventory of an e-commerce website. The system rules state that the stock quantity of a product cannot be negative. Suppose that initially, product A has a stock of 5 units. A customer places an order for 3 units, reducing the stock to 2 units. This process follows the rules, and consistency is maintained. However, if another customer tries to purchase 3 units of product A immediately after, the stock would become negative if not checked. To prevent this, the system must block this operation when stock is insufficient, or roll back the transaction to ensure the stock quantity never goes below zero. In MySQL, we can enforce such inventory consistency using several methods. The first method is using transactions. Here, we start a transaction, lock the stock record to prevent other concurrent changes, then update the stock. Based on the result of the update, we either commit or roll back the transaction. The second method is using triggers. This trigger automatically checks the stock before each update, ensuring that the stock does not drop below zero. If it does, an error is raised, and the update is prevented. The third method is using optimistic locking. Optimistic locking uses a version number to prevent concurrent conflicts. The update only succeeds if the version number matches. In conclusion, consistency acts like a guardian for the database, ensuring that even if an error occurs during a transaction, no invalid data is saved. Now let's talk about isolation, the I in ACID. Isolation is a crucial property of database transactions that ensures multiple transactions running at the same time don't interfere with each other. In other words, even when multiple transactions are happening simultaneously, each one should act as if it's running in its own separate, isolated environment. This helps prevent unintended interference and data inconsistencies. Why is isolation so important? In a multi-user, multi-transaction database environment, different transactions might read or modify the same data at the same time. Without proper isolation, these transactions could interfere with each other, leading to issues like dirty reads, non-repeatable reads, and phantom reads. To prevent these issues, isolation is often enforced through mechanisms like locks and version control, ensuring that concurrent transactions don't clash. Let's break down these issues. 1. Dirty read. A dirty read occurs when one transaction reads data that has been modified by another transaction that hasn't yet been committed. If the modifying transaction rolls back, the data read by the first transaction becomes invalid. For example, imagine two transactions, Transaction A and Transaction B. Transaction A starts and modifies the balance in an account from $1,000 to $900 but hasn't committed yet. Transaction B reads the balance before Transaction A commits and sees $900, using this incorrect data for further operations. Later, Transaction A rolls back, and the balance returns to $1,000. As a result, Transaction B used incorrect data, leading to inconsistency. 2. Non-repeatable read. A non-repeatable read happens when a transaction reads the same row of data twice and gets different results each time because another transaction modified and committed the data in between. For example, imagine two transactions, Transaction C and Transaction D. Transaction C reads the status of an order and sees processing. While Transaction C is still running, Transaction D changes the order status to shipped and commits. When Transaction C reads the order status again, it now sees shipped. Transaction C gets two different results when reading the same data, which is a non-repeatable read. 3. Phantom read. A phantom read occurs when a transaction retrieves a set of records twice with the same query, but gets different results because another transaction inserted new records that match the query. For example, imagine two transactions, Transaction E and Transaction F. Transaction E queries the database for all users over 30 years old and finds 10 records. While Transaction E is still running, Transaction F inserts a new record for a user age 35 and commits. When Transaction E queries the database again, it now finds 11 records. This is a phantom read, where the dataset changes between two identical queries within the same transaction. It's important to note the difference between non-repeatable reads and phantom reads. Non-repeatable reads involve getting different results when reading the same row of data multiple times, while phantom reads involve changes in the entire dataset based on the query conditions. How do databases handle these issues? Typically, databases support 4 levels of isolation. 1. RAD uncommitted, the lowest isolation level. Here, a transaction can read data modified by other transactions that haven't been committed yet, leading to dirty reads and other issues. 2. Read committed. At this level, transactions can only read data that has been committed, which avoids dirty reads but may still lead to non-repeatable reads and other issues. 3. Repeatable read. This level ensures that if a transaction reads the same row multiple times, it will always get the same result, preventing dirty reads and non-repeatable reads. However, phantom reads can still occur. 4. Serializable, the highest isolation level. It ensures complete isolation by making transactions execute in a sequence, one after the other, as if they were serialized. This level prevents dirty reads, non-repeatable reads, and phantom reads, but it comes at the cost of reduced system performance. Different databases have different default isolation levels. For example, MySQL usually defaults to repeatable read, while PostgreSQL, Microsoft SQL Server, and Oracle typically use read committed. SQLite, on the other hand, defaults to serializable. However, you can usually adjust these settings to suit the specific needs of your application. How to choose the right isolation level? Serializable offers the highest level of isolation, but has the lowest performance. Read uncommitted provides the lowest isolation, but the best performance. In practice, you'll often need to choose the appropriate isolation level based on your specific needs. For example, in a banking system, higher isolation levels like repeatable read or serializable are often required to ensure that account balances remain consistent during money transfers. In an e-commerce system, where multiple customers might place orders for the same product at the same time, using read committed or repeatable read along with optimistic locking mechanisms in the application layer can help balance performance and isolation, preventing issues like overselling or inconsistent data. Durability is the last key element of the ACID properties and is crucial for ensuring the safety and reliability of data in a database. Simply put, durability means that once a transaction is successfully committed, all changes are permanently saved. Even if the system crashes or suddenly loses power, the committed data won't be lost. Let's take MySQL as an example. When you perform a write operation like insert, update, or delete, MySQL does not immediately save these changes to the physical data files. Instead, for performance reasons, it first writes the changes to the redo log, a special log file that supports faster sequential I/O. MySQL then ensures durability by synchronizing the redo log to disk. Once this step is completed, MySQL marks the transaction as committed. Subsequently, MySQL will asynchronously write the changes to the physical data files. If the MySQL server crashes, it will check the redo log when it restarts. If it finds any transactions that were committed but not yet written to the data files, it will use the information in the redo log to restore these transactions, ensuring that all committed transactions are permanently saved. It's important to note that this explanation of MySQL's durability mechanism is a simplified model. The actual process is more complex, but the basic principles are the same. This way, MySQL balances performance while also ensuring data durability. Alright, we've covered all aspects of the ACID properties in databases. Atomicity ensures that all operations within a transaction either complete successfully as a whole or have no impact at all. Consistency ensures that the database remains in a valid state, adhering to predefined rules before and after the transaction. Isolation guarantees that concurrent transactions do not interfere with each other, and each operates as if it is the only transaction in the system. Durability ensures that once a transaction is committed, its changes are permanent and will not be lost, even in the event of a system failure. If you found this video helpful, please remember to like, share, and subscribe to the ByteVigor channel so you don't miss out on more great content. See you in the next lesson.